Okay, welcome to Chapter 8 of the class on multiple view geometry. Last time we talked about variational methods. I gave you a brief kind of introduction, very brief. As I said, I'm giving a class this coming fall on variational methods where we go more into detail about the background, about actually how to derive the Euler-Lagrange equation, etc. But for now, I guess for this class, it's sufficient that you have a little bit of an idea what these techniques are about. The key idea is that you set up some cost function or energy, often called, on the space of possible solutions to your problem. And one of the nice features of variational methods is that they allow to tackle what are called infinite dimensional problems. And the estimation of geometry is really a problem of infinite dimensions, because you can start with some arbitrary geometry and perturb it in infinitely many directions, so to speak. And so each of these is a separate degree of freedom, and so you have essentially, if you consider it as a problem in a continuous space, it's infinite dimensional. Of course, in practice, you always discretize. In the machine, you typically have to solve discrete finite dimensional problems. And so, for example, for the reconstructions I'll be talking about today, typically you discretize your space into a set of voxels, volume elements, and there may be, say, 300 cube volume elements. Each voxel can be part of the object or not. And so that is kind of a discrete representation of that the space of possible solutions. So there's 5 parts. The first part is I'll talk about variational multiview reconstruction, how to do multiview reconstruction in a variational framework, and how to use the concept of variational methods to tackle 3D reconstruction, to recover what's typically referred to as dense geometry. Dense means not, in contrast to what we've talked about in the class, not point clouds, just a set of sparse points, but the whole surface in 3D. I will then talk about some of, I thought that might be useful towards the end of this class to give you a little bit of an overview of some of the state-of-the-art algorithms of what's already possible today in the context of multiple view reconstruction. And who knows, maybe for one or the other among you, this may be an attractive starting point, say, for a master thesis, etc. For example, there's methods that can use photographs from the internet to do 3D reconstruction. This is quite amazing that nowadays to do computer vision you don't even need a camera. You just say there's enough image data on the web, and you use that data to do all sorts of fascinating things. Then I'll talk about real-time performance. Nowadays it is possible to get 3D reconstructions in real time as well. And I will talk about certain applications, for example, how to get dense geometry in real time, and how to do a navigation of quadrocopters, autonomous flying of quadrocopters using what's called visual SLAM, or structure from motion, so using a camera. 3D reconstruction is, mathematically speaking, if you consider the problem of dense reconstruction, so not point clouds but really surfaces, it is, the field is called in the mathematical literature shape optimization, because what you're trying to compute is a shape, the shape of things in front of the camera. And this is actually a very important and major challenge, how to represent shape, how to compute optimal shapes. When we talk about optimization, we want to represent shape in some way, and then we want to construct a cost function on the space of conceivable shapes. So that is to say, we don't know what the geometry of things around us is, but we want to assign some cost to every possible geometry. And so the first question is, how do you represent geometry in the first place? It turns out, among numerous representations of shape in mathematics in the literature, you can loosely group these into two classes. One are so-called explicit representations, and that is to say you want to represent the surface of the object, and you do that explicitly by essentially storing points that live on the surface. For example, you can think of it as a mesh, or in more general setting it would be some parameterized surface. So you have a set of points that kind of approximate the surface itself. That is the most intuitive, direct, it's a kind of a direct representation of the object surface. An alternative representation is the so-called implicit representation. And that is, rather than representing the surface of the object, you represent its interior and exterior. And one way would be, for example, to label the ambient space. So we label all points in 3D as, is this voxel inside the object or outside the object? And that would be an implicit representation, because by telling for every voxel, is it inside or outside, we implicitly represent the surface. That is the transition from inside to outside. One may wonder what the advantage is of doing that. Clearly, you already can get an idea. It's going to be more memory intense to label the ambient space, because the ambient space has 3 dimensions for surfaces, whereas the surface itself only has 2 dimensions. But we'll see that you can actually gain in certain aspects by reverting to implicit representations. Here is the explicit representation. I said a polygon is, or a polygon for 2D curves, you would have a polygon, or in a more general setting, you would have a parameterized curve. So you would have a curve like the one shown here, and you have a set of so-called control points, these black dots. And you can imagine if you move these points around a little bit, you perturb the whole surface in between. So this is a parametric representation of the surface, and that representation is extremely compact, in the sense that you need very little data to represent an entire continuous curve. The way you formulate this mathematically, just so you see this once on the slide, is by one example, I should say, is a so-called spline curve. So there is control points called Pi, and there is so-called spline basis functions Bi of S. And so although the curve is a continuous mapping from the circle to points in R2, so for every point on the S1 is the circle, for every point on the circle I have a mapping to a curve. Maybe I'll draw that. So here's your circle. Let's say here's 0, and then you loop around, and then you get 1 here, essentially the same point. And then you have a mapping C that maps each of these points on the circle to some point on that curve. So here, for example, we might have C of 0, and here somewhere we might have C of 1/2. So if I take that point, it's going to be mapped here. And that mapping can be represented as a linear combination of basis functions. And the basis functions typically look like that. These are so-called quadratic basis functions. There's also other kinds of basis functions. Doesn't really matter. They're localized. And this localization, see, for example, B2 is localized in this stretch of the parameter interval. And that means in this drawing that if I move that point around, if I perturb the coordinate Pi, this control point coordinates, then the curve in that vicinity will be affected. And the effect is actually just the effect is modulated by this basis function here. And if you take these quadratic splines, you get a smooth curve. If you take linear splines, that is just triangles here, then you get a polygon. Then essentially these points will actually lie on the curve, and you will have, so in other words, the spline curve is a generalization of a polygon. A polygon is You all know what a polygon is, of course. A polygon has a set of vertices, and then you move these vertices around. But if you're not happy with such a discrete kind of a non-smooth curve, you can just take higher order basis functions like second order. These are locally quadratic polynomials, and that has the effect of giving you a smooth curve. But otherwise, it's quite similar to a polygon. It's a generalization of a polygon, such where if I move a point around, I can change the configuration of the shape in that vicinity. That is one example of an explicit representation of geometry. Of course, this is only representing curves, but the way you represent surfaces, let's say you have a surface S, then you would have two parameters at S1 and S2, and then you would have a sum of Pij, Bi of S1, Bj of S2. And so then you would have a whole grid of control points that represent the surface, and these are points then in R3 if you want to represent the surface in R3. The basis functions are exactly the same, and that way you could represent with the sum over I and j. Each control point, it affects the surface modulated by the product of these basis functions, and that way you get. This is essentially a mapping from a grid. If you have an open surface, for example, you would have a grid, and it maps to some surface that is distorted form of the grid, if you will, in R3. You can probably imagine how every point Pij here is mapped to some point S on the surface. These are parameters, so these are, for example, in this case, this would be S1 and this would be S2. And so for any point on that regular grid, this mapping tells me where it is in 3D space. It's just a parameterization of that surface. And the idea is then that I can deform the surface by moving these control points, just like you perturb or deform the curve by moving a point on the image plane. Here, these points are in R3, and if you move one point, you can imagine that the surface is going to protrude in certain areas, or you can kind of make indentations just by moving these control points around. Very much like you have it in 2D, same thing works in 3D or any dimension. That's an explicit representation. Now here is an example of an implicit representation. In fact, two different examples. There's many ways to represent surfaces implicitly. These two representations are the most commonly used ones. This is why I decided to bring these up. The first one is a very simple one. It's just an occupancy labeling, if you want. You have the surface S, and then you can define for each surface an interior or an exterior. So if this is your surface in R3S, then this is the interior of S, and the outside is the exterior of S. And any closed surface always basically decomposes space into an inside and an outside part. And so what do? I define a function u that just labels the inside with 1 and the outside with 0. You can do it the inverse if you want. This is just a convention. It's just a binary labeling that encodes the surface implicitly. And the idea is that any surface S, any closed surface, can be represented by such a binary labeling. In fact, there is a obviously direct one-to-one correspondence between closed surfaces and binary labelings. Any binary labeling corresponds to a closed surface. Any closed surface corresponds to binary labeling. One of the advantages to mention that up front of implicit representations is that the so-called topology of the surface is not fixed. It can be anything. For example, what I can represent, if this is my space, I can represent objects that are not simply connected, or not connected at all. For example, if my surface S has multiple components, which may happen, it doesn't matter. Here I have U equals 1, U equals 1, U equals 1, and outside U is 0. So I can represent any number of components with a single binary labeling. And this is very useful. That does not work if you have a parametric representation, because if you want to map multiple objects with a single grid, it's not going to work. You'd have to split the grid first. Whereas here, it doesn't matter how many components the surface has. It doesn't matter whether it's a spherical object or a torus-like object, so whether it has holes or not. For implicit representations, they don't care. They just label the ambient space. And in terms of computation, that is an extremely helpful aspect. Because if you do 3D reconstruction, you don't know beforehand whether the object has the topology of a sphere or of a torus or something, so whether it has a hole or not. And so if you work with implicit representations, they don't care. We'll see examples in a second. Another implicit representation that is slightly different is, instead of representing the ambient space and labeling it just with 1 and 0, I can do something more informative. I can label every voxel X by the distance it has from the surface. And then by convention, I will use the positive distance from the surface inside and the negative distance outside. That is a different representation. Mathematically, let's draw that on a 1D line. If this is my space omega, and I want to represent a surface S that lies here, rather than representing, as we did before, a binary function that looks like that, 0 and 1 inside, let's say here is the interior, I can represent the surface with a function that looks like that. So that tells me for any point X, how far is that point from the surface, and that is the value of phi of X. Phi of X is called a signed distance function. A distance function is a function that encodes the distance to some structure. So phi d of X and S, that is the Euclidean, typically Euclidean distance from the surface S. The signed distance function just means I put a negative sign outside and a positive sign inside. Turns out, so one of the things, if you want to represent geometries in this way, is of course the question, given some surface S, can I actually compute that distance function? And that actually can be done. It's very efficient. Not surprising really, because what I have to compute for any point, so for example, if I want to represent a curve in R2, I have, for any point, I have to compute what is the distance to the closest point on the surface, on my surface S. And so this is closely tied to the question of shortest path computations. And indeed, the algorithms you use to solve the distance map estimation, to compute the distance map for a given surface, the algorithm is essentially a shortest path algorithm. Yes?
Is there a surface for every distance map?
Yes. Yes. The way you can actually extract the surface from the distance map, so this is the distance map from the surface, and the surface from the distance map, you would just say the surface are all points X in omega such that the distance map changes sign. So such that you would say phi of X equals 0. So the points X where the distance map is 0, that is the surface points. Numerically, how would you go about computing it? Say I give you a signed distance function, some labeling of the space, and each voxel is assigned some positive or negative value, you just go through it, sweeping from left to right, let's say, and you check when does it change its sign. So, yes, you get a connected closed surface in this way. So of course, you know, phi in numerically is never going to be exactly 0, but what you're going to do is you're just going to go through your grid. Let's say here's your discretization, your grid, and then you go through it and you say here phi is negative, here phi is negative, here let's say it's still negative, and then at that voxel it becomes positive, so you know, or here it becomes positive, so you know the surface is going through somewhere between these two. And then you can just mark that as a surface element, and you can... The nice thing is you don't actually have to do that in MATLAB, everything is there. Yes?
How can we actually compute it if phi is dependent on S and S is dependent on phi?
Yeah, so it's a good question. So here the idea is, if I give you a surface S, what would be the sign distance function? And then you would call a function called BWDist in MATLAB, and that computes the so-called Euclidean distance function. It computes the function phi, it determines for any point how far it is from the surface. So this is not, we're not optimizing shape yet, we're just saying, given some shape, how could we represent it with a distance function? Or, in turn, given a distance function, what shape does it represent? And this can also be done in MATLAB. It's called isocontour. There's functions that basically read out the isocontour for level 0. So the function where phi is 0. So here you can see it. You would just walk along the grid until the function phi changes sign, and then you know that is for that basically ray. I have the surface here, and you would do that, you know, line by line, column by column, and that way you could mark the surface off. It's a numerical process, of course, and there is a certain approximation, so you can only get the surface up to the pixel accuracy. There is an argument, some people say one of the nice features of distance functions is you can encode surfaces on a subpixel level. This is possibly an advantage over the binary labeling. If you do just a binary labeling, 0, 1, then if that pixel is 0 and that pixel is 1, you know the surface is somewhere in between, but you don't have an idea where. Whereas if you actually encode the exact distance from the surface, you have a subpixel accuracy about where the surface is. So these are two possible and popular representations or implicit representations of surfaces: the binary labeling, the signed distance function. Maybe a few words about what the advantages and drawbacks are. I've already mentioned it, implicit representations require more memory, typically. Because you have to label the entire ambient space, and essentially that space has one more dimension. The surface is 2-dimensional, the ambient space is 3-dimensional. And even if you represent surfaces in higher dimensions, sometimes that is necessary, then implicit representations always increase the dimension by 1. And so they always add to the memory requirements and sometimes also to the computational load. Because to propagate and move a surface, in the explicit representation, I just take the points of the surface and move them, and that moves the whole surface. In implicit representations, I have to update the entire volume labeling, and I change the labeling, and that implicitly deforms the surface. So moving and updating implicit representations tends to be slower. I don't just have a few control points, but I have, or the entire ambient space needs to be updated. I should say there are efficient ways to do that, both in terms of memory and in terms of speed, so-called narrowband methods, where you essentially only label the ambient space in a band around your surface. The rest, you know, it's not going to change, and so you don't care. But that's also programming-wise a bit intense to implement, because you have to keep track of where is my band, which voxels are the ones in the vicinity of the geometry. And you need to possibly, if the curve moves, you need to update the band that you propagate along with the curve. But implicit representations have many advantages, and one is that you don't have a choice of the parameterization that the representation depends on. One of the problems with explicit representations is you can imagine there are many ways to represent a surface explicitly. For example, already with the curve, I was saying maybe C of 0 is here, but I would get the same curve if I was to say C of 0 is there and C of 1/2 is over here. So you have an invariance of the geometry to reparameterizations. In fact, I can reparameterize the circle in any way and the mapping will still give me the same geometry. And that is mathematically a bad thing usually. Whenever you have a non-unique representation of the object of interest, it's not good. See, here you would have infinitely many representations that all basically encode the exact same curve or surface. That is not good, because when you're working with these, you have to make sure that they're actually identified in the algorithm. That these two representations, they actually represent the same thing. And so with implicit representations, for example, if you have a binary labeling of your ambient space, you know, there is no ambiguity, there is no redundancy, there are no multiple representations of the same structure. And I mentioned it, the topology is not fixed. You can represent arbitrary topology, so any number of holes. So you can start with a sphere, and if you just label the ambient space, then it's easy to make a sphere split into multiple spheres, into a torus. You can create holes just by relabeling the ambient space. Changing certain values from 1 to 0 has the effect of removing structure there, and then you create splits, which is very hard to do in parametric representations. It can be done. You can program splitting methods for parametric representations, but it's not a nice thing to do. It's very tedious and somewhat heuristic. A last aspect, and we'll see that in a second, is once you have implicit representations, often shape optimization problems become convex. And this is quite fascinating. And as you know, from an optimization point of view, convexity is good. Convexity means you can compute globally optimal solutions. And we'll actually see that now in a second for the problem of multiple view reconstruction. And what I want to start with is just to give you a glimpse of how can you formalize multiview reconstruction, the reconstruction of dense geometry, as an optimization problem. For now, we will assume that the camera orientations, so translation and rotation, are given, so we don't have the structure and motion problem, in the sense we don't want to compute the geometry and the camera locations. We assume somehow magically someone gives us the location and orientation of each camera. There are two ways to get it in practice. One is that you have a camera set up that you calibrate beforehand, and that is commonly done if you want to do action reconstruction. You would set up a set of cameras in the room all around, and then you can calibrate them at, you have enough time to figure out where is each camera, how is each camera. You can walk around with a calibration, so-called calibration rig, a pattern where you know what it looks like, and you can check how is that represented in each image, and then you can calibrate all cameras in this way. And then you know where they are, and if you don't move them around, but just reconstruct the geometry later on, then you have these parameters. An alternative is that you use image data, and we'll see that in a second, to estimate the camera transformations, much these algorithms that we talked about in the class, 8-point algorithm, bundle adjustment, things like that, to compute the camera parameters. And once I have these, I can then use this approach to estimate dense geometry. The way this works is you ask yourself how likely is a voxel on the object surface. So to give you a drawing, let's say I have some surface S that I observe in multiple views. Here is one view, and I say how likely is a given point on the surface. If I know the projection matrix, as I say, I know where the cameras are, I can project that point into the first image, and I can also project it into subsequent images. If that point is on the surface, I should be seeing the same color here. And since I have these projection matrices, I can easily, for any voxel X in that space, I can simply project it into the pairs of images. And then I can check the color consistency. Do I see the same color, yes or no? And I can assign what's called a photoconsistency function. So V is my volume, that is the space here where I want to reconstruct. And I can say if I see the same color, then rho at that voxel should be small. So here it should be near 0. Whereas if I see a different point, let's say a point that is not on the surface, maybe this voxel here, I project it into pairs of images again. I see colors here, and I check, are these colors the same? And in general, they will not be, because that color is actually the color of this surface point, whereas this color is the color of that surface point. So we see the colors will not match. And so we can assign to that voxel here a value of rho that is near 1, let's say, some large value. And that can happen indeed. If the colors are the same, then this approach is not going to work well. When is that going to happen? It's going to happen in particular if the object is entirely uniformly colored. So if you live in a purely white world, object, background, everything white, then all colors I see are going to be white. And then the colors will always match. Then I cannot have color consistency. Or I always have it, but it doesn't tell me anything about the geometry. So in other words, the assumption that you're pointing at here is that the world is sufficiently textured. And then there is a chance that these points actually do have the same color, but it's not very likely. They may be for this particular voxel, but then for the voxel next to it, most likely I will see at some point a color difference, and then I will have high value of rho if I don't see the same color. So it is quite right, low values of rho do not always mean the surface is there. And high values, and so as a consequence, I have to be somewhat cautious how to interpret that. I cannot just label all points with low values of rho. That's not going to give me a meaningful reconstruction. But the idea is that points on the surface should have small values of rho. Points that are not on the surface should typically have larger values of rho. Not always, but generally, let's say. Up to some exceptions. The exceptions are if the object is uniformly colored or if it has a repetitive texture. That can happen. Often objects, will see examples, have repetitive textures, and then chances are every now and then you will see the same color, although the points are not consistent. How do we formalize the optimization problem? Quite simply, we say, find a surface S in that 3D space, such that if I integrate this photoconsistency over the surface, it should be small, because small means good color match. And integrating, as you may remember, just means I sum for all points little s on the surface, large S, I sum the values of rho on this surface. And so for that given surface, the one I drew here, I can simply compute rho for all points on the surface, and the accumulated cost is my energy. And if that energy is low, then it's a good surface. Then it means all points are photoconsistent, or most points are photoconsistent. Whereas if the energy is high, it means it's a bad surface. And so clearly now I have a cost function that allows me to distinguish a good reconstruction from a bad one. This is a formulation that was proposed by Faugeras and Kiriven in '98. It's been used by many others. It's mathematically, this is called a weighted minimal surface. If you just integrate all surface elements over the surface, so without the rho here, you get the surface area. It's a sum over all points on the surface that gives you the area. If I weight this sum for each element on the surface, I weight it with the photoconsistency, it's a weighted minimal surface. Very much like a weighted shortest path. It's a generalization of weighted shortest paths to 2D, to surfaces. The way this energy was traditionally solved is by local minimization. You start with some initial surface and then you locally perturb it so as to improve the photoconsistency score. This could be called a photoconsistency score. The problem with this energy is, although it looks very beautiful and it is rather simple actually, there is a major drawback, and that is that the global minimum, now that if we talk about optimization, can we actually compute the global minimum? In this case, we can easily compute it. In fact, the empty set is the global minimum. Right? Because if I'm integrating or summing the photoconsistency function over all points of the surface, if I have fewer points on the surface, I get a smaller value, and if I have no surface at all, I get zero cost. Right? So this is sometimes called a shrinking bias. Smaller surfaces are preferred, up to the extreme case that if I take no surface, I get zero cost. And the issue is that function rho is always non-negative. So no matter what surface you take here, it will always have a non-negative cost. You can never get below zero cost. In other words, a solution that gives you zero cost is the best you can ever do. And the empty set gives you zero cost. And that is a simple proof that shows the empty set is a global minimum. May not be the only one. If you really have a whole surface S where rho is exactly zero, then the integral over that surface will also be exactly zero. So you may have non-trivial solutions that are also globally optimal. But that in practice is unlikely. If you do measure color consistency, you will never get exactly zero. You will never get perfect matches. And so rho will typically be larger than zero. So this is an issue. It means that somehow this approach is fishy. It doesn't really work. It doesn't work if you tackle it in terms of global optimization, because you get the empty set. So one of the things that we proposed in 2008, this is then the journal version of this approach, is to say, well, clearly the empty set is not a good solution. I see an object in every camera, in every image, and the computer tells me there is no object there. Clearly that is not matching my observation, let's say. And so the question that we asked is, can we use the same weighted minimal surface approach, here it is, the integrated photoconsistency, but impose as a constraint that there should be an object there in the scene. And the way we impose it is we say, well, let us assume that in each image we actually see the silhouette of the object. So here's our object, and what we have is the area in the image that corresponds to the object. So the assumption here is that we are observing some compact object that has limited dimension, and so we have the area of the surface here, and then we can say we want a reconstruction S such that if I project this into the image I, so that would be the projection pi I here, it should match the silhouette SI. And we can impose that constraint for all n images. In the computer vision literature, this is called silhouette consistency. I want a reconstruction that is consistent with the object's silhouettes. And this is then an optimization problem. You would call it a constrained optimization problem because you have a cost function and you have a set of constraints. This is a non-convex optimization problem as a function of the surface S. So if you try to move a surface so as to improve the score here, you will get stuck in a local minimum. This is not surprising because you will have points of low rho all over the place because colors may every now and then match. That gives a low value of rho and the surface will be attracted to these points. It may not be the best configuration, but you will get a locally optimal one, and then if you keep moving it, the energy first goes up before it goes down again. So this is clearly a non-convex problem, but it turns out you can convexify it by moving or reverting to implicit representations. And here's the idea. So now I use a binary labeling of space. This volume occupancy function that tells me 1 if the voxel is inside the surface, 0 if it's outside the surface. If I use that representation to represent the surface, then this optimization problem as a function of the surface S can be shown to be equivalent to this optimization function as a optimization problem as a function of U. Maybe to show you a little bit why that is, here we have the gradient of u, that is the derivative of u. U is a binary function. As I said, it's 1 inside and 0 outside the object, right? So here we have u equals 1, outside we have u equals 0. That means the gradient of that function is 0 most of the time, because the function u is constant outside. So here at that point the gradient is 0. It doesn't change. Inside, the function u is 1. It doesn't change. It's also 0. The only points where the gradient is non-zero is on the surface. And on the surface, the function u jumps from 0 to 1. And it turns out, this can be shown, that if you integrate the gradient over the whole volume, so this is d3x if you want to be precise, I'm integrating over the whole volume. If you integrate that gradient, it's 0 except on the surface, in such a way that it reproduces exactly the integral over the surface. And so what I do here is I take the photoconsistency at any pixel, any voxel x, and I weight it by this gradient. And that masks out all points that are not on the surface, and it only leaves the points that are on the surface, such that this is exactly the same as that. This is called a weighted minimal surface, as I said. This expression here is called the weighted total variation, because this function, integral of nabla u dx, is called the total variation. Total variation of the function u. And what we have here is clearly just a weighted version of it, where at every voxel I just weight the gradient by rho. One of the things that is known for this cost function is it's a convex cost function. This is not surprising because the gradient, the norm here that you see here, you all know what the norm looks like for an argument s. The norm of s just looks like that. That's a convex function. This is the key reason why the total variation is convex. In addition, you have a weighting with some positive term that doesn't affect convexity. If rho is non-negative, that preserves convexity. And you have a summation or integration over all points, but summing convex expressions preserves convexity. So there's a lot of nice properties of convexity, such that if you have two convex functions, the sum is still convex, and if I sum over lots of convex expressions, it remains convex. So we have automatically obtained a convex representation just by reverting to an implicit representation of geometry. And this is what I mentioned earlier, that using implicit representations you gain in terms of convexity. Now these silhouette constraints, they're somewhat abstract here. The projection of S should match into the image should match the silhouette. Let's look at what that means precisely. It basically means, let's say, here's the object and here are the volume elements. If I see a pixel that is part of the silhouette of the object, of the interior of the object, then the visual ray going through that pixel must intersect the object somewhere. That is essentially the constraint for that ray. For a ray that passes through the outside, so outside the silhouette area, I know this ray cannot intersect the object anywhere. I see background here, I don't see object. That means all points on that ray must be background. There cannot be any object in the line, in that line of sight. So these are really the two constraints that it boils down to. And I can represent them if Rij is that ray through pixel j of image I, if you will. Then I'm saying if that pixel is in the silhouette area, then the integral along that ray should be at least 1. There must be at least one voxel that is on in that sum. Whereas if the pixel is not in the silhouette, then the integral is exactly 0. So these are the two constraints. There are lots of these for all images and for all pixels in each image. Tons of constraints, but doesn't matter. What is important here is these are linear constraints. And so in the space of solutions, if this is my space of solutions, then for example that inequality constraint basically separates the space of solutions in those that are feasible and those that are not. And if I have multiple such constraints, I will have another constraint saying the feasible solutions should be on this side, then I will have another constraint, and so what I end up with all these linear constraints is some convex set. Because linear is in particular convex. And so what this means is that the set of configurations that fulfill these constraints is a convex set. What I should mention is the only aspect that makes this problem, the entire optimization problem of minimizing this cost function under these constraints, the only thing that makes this non-convex is the fact that the function should be 0, 1 labelings. The space of functions that label into 0, 1 is not a convex set. The way you can see it is if you take two functions that label space by 0 and 1 and take their weighted average, what you get is a function that is not necessarily 0, 1. It may be 1/2, for example. If you have the average of two functions, let's say one function is 0 at a voxel, the other one is 1 at that voxel, the average will be 1/2. And so you can see just by interpolating two binary functions, you get some non-binary functions. And that violates convexity. Remember, one definition of convexity says that if you have two functions in your solution space, then all points in between on that connecting line should also be in the set. If I have two binary functions that fulfill these constraints, and then I interpolate, then I'm no longer in the set of binary functions. So the question is, what can I do? And this is what is called convex relaxation. I have an optimization problem. Relaxation means I just drop a certain constraint and say, oh, you know, that's a difficult constraint. I don't know how to encode it. Just forget about the constraint. Forget about it means you allow U to take values in the interval from 0 to 1. Then you have a convex set. That's called the convex envelope, or the convex hull. Sorry, the convex hull of this set is the set of functions that take values between 0 and 1. Because then if I interpolate, if both functions have values between 0 and 1, the convex combinations will also have values between 0 and 1. And so the fact that I really want a hard decision for each voxel, I want to know, are you object or are you background? I will loosen that and say, You know, I want some real valued labeling of each voxel that tells me, loosely speaking, how likely is that voxel object or background. And so what I end up with as an optimization set are functions that take values in the interval from 0 to 1 and that fulfill these two sets of constraints. And that set is, by construction, one could say, a convex set. Because the only aspect that made it non-convex, this integrality constraint, I dropped that constraint. And I said I allow intermediate values. So I'm not actually solving the original problem anymore once I use this representation, but it's something like a soft labeling of rather than a hard labeling of object background, I do a soft labeling. And with that, and then what I do is I solve that convex problem. A convex problem can be solved optimally, and then I reintroduce the binary labeling just by thresholding the solution. So I have a real valued labeling of space, and then I say any voxel that is above a certain threshold, where u is above a certain threshold, I set to 1, and any voxel below a threshold, I set to 0. And that way I get a hard decision. In other words, what I do is I compute an isosurface of that function u, an isosurface of that threshold. So the surface is exactly those points where u is at a certain threshold. So I'm using the fact that values near 1 indicate that it should be object, and values near 0 indicate that it should be background. And then I set some threshold in between to determine which parts I make object and background. And with that, what I get is an algorithm that reconstructs dense geometry, and I don't need an initialization because I'm minimizing a convex energy, so it doesn't matter how I initialize. Here are 3 out of 33 input images taken from a standard camera. This dataset can be downloaded online. It's a dataset provided by Yasu Furukawa, and it provides also the camera parameters, so it is a calibrated image set, which is good because it means you can do multi-view reconstruction. You don't even have to calibrate cameras nowadays. You just go online. There's enough datasets where people have done that for you. And so we use this, and these are some of the reconstructions we computed in this approach, and you see that we get a lot of fine scale details in the reconstruction. Here's another example. This is actually a data set we acquired ourselves for a museum in Bonn. We walked around this statue with a digital camera and just took a set of pictures, 28 images. This is the reconstructions that we computed. And so you see very nicely all these folds in the clothing, so you can actually recover a lot of details. And as you see, these are not point clouds, but really dense surfaces by construction, because what we compute is a labeling of space. Any voxel will know at the end, am I object or am I background? If you do point cloud reconstructions, you don't have that knowledge. And let's move on a little bit to see what else is being done. So, and what I'm showing you now are more kind of a short overview of what the state of the art is today or over the last years. This is a paper that appeared in 2008, and it's called Modeling the World from Internet Photo Collections by Noah Snavely, Seitz, and Seliski. Steve Seitz is on the West Coast. Seliski is with Microsoft, Rick Seliski. What they proposed is to use the internet. They said there's tons of data on the internet, there's tons of images in particular, and there are data sets where in the images the intrinsic camera parameters are stored. So good digital cameras, when you take a picture, they store the value of the focal lengths, etc., because they know what the focal length is. And so once you download the images, you not only have the color, but you also have the information about the focal settings. And that way you can remove that calibration. This is an important aspect because it means that you can work in the calibrated setting. You know the calibration parameters. As I said, the uncalibrated setting is a little more challenging, and I was always saying if you have access to the calibration parameters, use them. And a lot of images have them, and so there's databases like Flickr where you can download calibrated images, and what you do is you just insert a search query term like Notre Dame, and you get tons of images of Notre Dame, thousands of images. And so one of the challenges here is actually not so much to not only to reconstruct given images, but to pre-select what are the best images to use. And you can do that, and there's a lot of sophisticated algorithms to figure out, are these useful images for my problem? For example, there's algorithms that check the overall color consistency among two images. Do they have the same typical colors? If yes, there's a chance that they actually correspond. If not, just throw away the one that doesn't match. And so there's one challenge is to prune these thousands of images and pre-select ones that are likely to work well. There's a lot of, I should say, heuristic strategies. What you do then is you extract feature points and assign a feature vector to each point that characterizes that point, ideally, uniquely in a way that even in a whole set of images you can figure out, have I seen that point before? And you do that for many points, and then you have some sampling strategy to figure out how likely do these two images really match, and you prune and just use those where you have a good match. And the good thing is in that regime you have enough images. If you don't get a sufficiently good correspondence or match, just forget that image and use the next one. For example, when people take images of Notre Dame, chances are that in most images, some person is in front of the image and say, hey, mommy, I'm at Notre Dame, right? That's very nice, but it doesn't help the reconstruction because you don't have that same person on the other images, and if you do, it's not in the same, pose, and so that's not very helpful. So you want to make sure you only get images that actually reflect the structure you want to recover. Yes. So here's what you can do, and this is what they proposed, is ideally the thing is automatic in the sense that you give in a search term and it recovers point cloud reconstruction, and what you see here is the set of cameras, and now I'm going to show you a set of videos that actually do run, it seems. This is a reconstruction of Rome, and you see they basically plugged in the search term Rome, and these are reconstructions, and all these little things here are camera locations. And it looks very good. One of the challenges that Noah worked on extensively is how to make the visual appearance look. How do you blend in between two views? You see he uses the colors from the images and he encodes the voxels with their respective color. Here's another example of Dubrovnik in 3D. It's a nice town. One reason why they chose Dubrovnik is it's a fairly small town. And so it's a nice, beautiful town. It's also fairly small. And so you can recover the entire town, which you cannot do with Rome at this point.
Do they use variational reconstruction?
Here, no. So this is more using I would say classical pipeline, where you do point correspondences very much like we talked about, and then something similar to an 8-point algorithm to get an initial guess about the camera locations. Then they additionally do bundle adjustment to improve the camera locations, and the software that Noah provided is called the bundler. It's called bundler because it includes as one component bundle adjustment. And the nice thing is you can download that software, you can run it. We use that, for example, for the museum reconstructions. We used Noah's bundler software to estimate the camera parameters. Because what you see here, it looks nice, but it's not a dense reconstruction. It's just point clouds. So there is no notion of a surface, and so that aspect is not solved here. Yes?
How the problem is solved when similar pictures can be taken from different perspectives in different presentations?
Yes, so the question is if you have a different perspective projection, if you have different intrinsic camera parameters. What you can do is you can remove these beforehand by pre-calibrating. You have this matrix that we call K that contains the calibration parameters, and you can multiply, essentially you multiply with K inverse to remove that these transformations. Yes.
And they most probably don't contain some parameters.
Oh yeah. So what they, yes, very good. So if you have no camera parameters, this is going to be more difficult. Then you have to work in the uncalibrated setting, and then all you can expect is these reconstructions about up to a projective transformation. What I mentioned in that one chapter about uncalibrated reconstruction. So here they always use images that have calibration parameters. But there is still a challenge, you know, sometimes if you insert, as I said, some images don't match. Possibly, you know, you have an artist that painted Notre Dame, and then you type in Notre Dame and you get his oil paintings. That's not going to be helpful, especially if there may be more abstract oil paintings that are not metrically consistent. There are people, mind you, that actually work on the problem of putting into correspondence paintings and real pictures, and trying to model the variability that you have in a painting in a way that you can actually maybe do 3D reconstruction from paintings as well. So these are things that people are working on with some success. Yes. So this recovers point clouds, and it recovers the camera parameters. And for example, you could now use these camera parameters and the image data to do dense reconstructions, and people have worked on that as well. Here's another example. The bundler is that I just mentioned, Noah Snavely's bundler, gives you accurate camera parameters, but it's not real-time capable. It's actually fairly intense, especially one of the challenges if you want to reconstruct a whole town is it takes a lot of processing time. And so one of their papers is called Reconstructing Rome. There is a follow-up paper with a nice title of Reconstructing Rome on a Cloudless Day. And what it refers to is you want to do it without using a computer cloud. Because the first paper on reconstructing Rome used an entire cloud of computers to actually process that. And they said we can do it without a computer cloud, so they called it Reconstructing Rome on a Cloudless Day. And so there is a challenge, and day means that really the challenge was, can we get the solution within 24 hours? In certain applications, you cannot wait 24 hours. You want something that is more real-time capable. And so very recently, starting, well, actually the first real-time capable structure and motion algorithms appeared in 2000. This is a work of 2007. What's nice about this work is, the nicest part is the code is online. You can download it. So one of the good features in research and science is many researchers put their codes online. We also do to some extent. And that, you know, promotes research because you can build up on it. And I'll show you some of the things that can be done. This is a framework called PTAM. PTAM is an acronym, and it stands for Parallel Tracking and Mapping. Here you see the terms are slightly different. We talked about structure and motion. Tracking is the motion. Mapping is the structure. So it's very much like SLAM. You see yet another slightly different term for the same thing. What it does is, you can already see this in one image, it tracks points. So this is a little bit the classical pipeline, but made real-time capable. The way it works is actually these linear algebra type algorithms that we talked about, they are real-time capable. They're quite fast. These factorization approaches using singular value decomposition, etc., are quite fast, but they're not very accurate. And to get a very accurate and robust reconstruction, you need to do bundle adjustment. You need to do this nonlinear optimization. But that is not real-time capable as of yet. And so what they did is they had an approach that does a fast version to estimate the camera location roughly in real time, and then on a separate thread in the background they did bundle adjustment for a certain set of keyframes. So you don't do bundle adjustment for all images. The challenge in real-time performance is you get 30 images a second. And so if you have a minute of recording, you easily have thousands of images. And you cannot do all of these with bundle adjustment. But so you have to select carefully a set of keyframes. And then for these few keyframes, you can do bundle adjustment on a second thread in the background. And so you have a current estimate of the camera that is fairly accurate, and you have a reconstruction of the scene that is getting more and more accurate with time through this bundle adjustment that runs in the background. And the nice thing is, since you run it in the background, you don't have to have the bundle adjustment done 30 times a second. You can just keep running it in the background, and for any given frame, all you need is the current estimate of the camera, and that you only need roughly as long as the overall reconstruction is accurate. So this is the key idea in the PTUM. It's actually quite clever, I find, and we found the algorithm works fairly well. As always in research, when it came out, people were saying it works super well. You know, then research advances, then people try to reproduce that, and then they see, oh, one can actually even do better and get more accurate or more robust. But you'll see, this is already quite nice, some of the things you can do. It was published at the Symposium on Augmented Reality. And this is what they do. They mostly use this approach to track the camera. So you see that they actually have points and they have some sparse reconstruction, but nowadays PTUM is mostly used to get real-time estimates of the camera location. Here are these points. The different color codes tell you something about what type of feature point is tracked here. And what you see here is this grid is actually superimposed into the world, and what you saw is it remains stationary. And so this grid is fixed to the world, and it shows you how good your camera tracking is. If the grid jitters, it means the camera tracking is suboptimal. But you can see you can superimpose things into this world, and this is what Georg Klein, this is a work of Klein and Murray. And Georg Klein, the first author here, he's an extremely creative character, so he generated a lot of funny things. This is in Kyoto on the train, so he has a camera pointing outside, and then he can, in real time, while the camera is running, superimpose virtual objects into the scene that look like they actually stand in the real world, but they're not. Here's another example on the train. And so this is actually real-time screen capture. So while you hold your camera, you see objects that are superimposed into the scene. This is one, it actually very well displays what augmented reality was supposed to do. And we see that structure and motion algorithms, if they're real-time capable and robust and accurate, you can do tons of things. This is a stone garden in Kyoto, and here he has a handheld camera, and in real time he can superimpose, you know, his favorite Ewok rampage. So there's Darth Vader fighting the Ewoks, and it really looks, you know, you've all seen that in Hollywood movies, right? They can superimpose characters into real videos. This does it online, so that is very different from Hollywood. Hollywood today is not online. They don't need to have it online, you know, they can process for days, for weeks, for months until the movie comes out. But the nice thing about this here is it actually is on the fly while you're taking the video in real time. It basically inserts objects. And this is very nice. I should say the first time this was done, to my knowledge, is a paper by Jin Favaro Soato in 2001. They had object insertion, 2001. Real-time object insertion, they call it. So it was somewhat similar. They didn't put the code online at the time. This here has the code online. It's different from what they did. This separation of bundle adjustment that runs on the background and real-time camera tracking in the foreground. That is, in my view, one of the novelties of this PTAM approach. But you see, you get in real time the camera trajectory. And that is amazing because it allows you to do tons of things. So one of the things you can do is you can try to do, and this is what we did in a master's thesis in 2010, we said, can we do real-time dense reconstruction? And it's actually not so difficult. What we set out to do is fairly straightforward with what you've already seen in the class. We set up a cost function that, I admit, again, looks slightly complicated at first glance, but you've seen the components before. This here you've seen, we want to compute a height map. So H is a height map, meaning for any point on the image plane, we want to determine where is it in 3D. So that is these lambda parameters, we always call them in class. It assigns to each pixel on the image plane a depth, a distance from the camera. And what we have here is the total variation. So we say from one pixel to the next, that depth should not change too much. It should be a smooth surface. That is the assumption that comes in here. And what do we have here is very much like the optical flow cost function. We want the colors to match. So we are saying, if I see a point here in this image and I see it in that image, I want the colors to be consistent. So I call this color I1 for the first image, and for the eyes image I call this II. How do I get from that pixel to this pixel? Let's call this pixel little x. Then that point, remember, was just h times x, the height times x, if I'm in homogeneous coordinates. Then I rotate into the new camera coordinates with my rigid body transformation gi. I have that now. I don't have to compute it. PTAM gives me the camera coordinates. So it tells me what is the rotation and translation of the camera. So I can rotate and translate the 3D point into the coordinates of camera I, and then just back project. So pi is that generic back projection. And then I say the color I see here, at that point, the transform point into, so I transform from the point in the image plane of the first image to the image plane of the eyes image. And these colors should be the same. That means the distance should be small, meaning this cost should be low, that error, this discrepancy of, so it's something like a photo consistency. But the difference is I don't compute a flow field to determine point correspondence and then estimate a 3D model. No, I can directly estimate a 3D model, a depth map H, such that the colors match. And so I say, so this is not parameterized in terms of the displacement or the correspondence vector, but it's directly parameterized into that height map. Give me a height map H such that if I then transform it into project back into the other image, I see the same color. And what I say is do that for all pixels. So find one height map H that for all images 2 to n makes them color consistent with the first image. And it turns out that one can minimize this cost function efficiently using coarse-to-fine strategies. Linearization means this is a non-convex cost function, and so we just linearize locally to say we have a small depth, and we do that on multiple scales. This is the coarse-to-fine, and it turns out if you parallelize this on graphics cards, it runs in real time. You can run it at 30 frames a second. And what you get is these kinds of reconstructions. So this is one view of the input. This is the reconstruction. Here you see it's a dense surface, so we have surface everywhere. Of course, this parts of the surface here that are not very visible from that viewpoint, the reconstruction is not going to be very accurate. There's a certain smoothing over the unobserved parts of the scene. You can see that slightly here. You'll see it in the video a little more. And then you can superimpose the texture from the input images, and this is what you get. So you get a textured, dense 3D surface at frame rate. And the nice thing in this context is, since the dense reconstruction is computed in real time on the GPU, we can use the CPU to run the PTAM in parallel. So the CPU runs PTAM, it gives you at any given moment the camera parameters, and then on the GPU in parallel we can compute the dense reconstruction. And so we have the geometry, the camera motion from PTAM using sparse feature point approaches, and then the dense reconstruction from the graphics card. Here's other examples, like a desk scene with the monitor, and we actually zoomed in. There's a certain, you see here as well, slightly over smoothing that comes through this regularization, through the fact that we say from one point to the next, it shouldn't change too much. But you can see the structures, even in zoom-ins, you can see the different structures in the scene. This again is the untextured reconstruction, and this is with the texture superimposed. Here's a video. So this is the input image. It turns out you don't actually have to move the camera a whole lot, just a little bit back and forth, left and right. And this is the reconstruction. In the beginning it looks very bad because we don't have many images. In an online approach, the images come with time, and the more images we get, the more it stabilizes to some dense reconstruction that you see while you're moving the camera.
Is it getting better if you capture more frames?
So one of the things that needs to be done, and that in fact has been done after in 2011 by Richard Newcomb, had a paper in 2011, sort of a follow-up paper where he integrates these multiple depth maps into a coherent 3D model. See, a depth map, strictly speaking, is not a full 3D representation. It's just a height or depth map. If I keep moving the camera around, I have to fuse all of these different depth maps into one coherent 3D model. And that's been done, and that is currently done, so this is where the state of the art is today. And then it gets better. For example, here we have an over-smoothing because from this viewpoint we haven't actually seen anything here. So if we keep moving the camera around, we get a new reconstruction from that vantage point. It should ideally all be fused into a single 3D model. And that's currently being done, and this is to some extent still an open challenge though. This is basically where we stand today. One of the difficulties, maybe to mention why that is a challenge, is a depth map is mathematically a very different representation from a 3D volume labeling, and so to convert from one representation to the other mathematically is a bit involved, and that complicates the programming, and it also complicates, increases the runtime, etc. One of the things, maybe the last thing I wanted to talk about today, is once you have PTAM, you can do all sorts of cool things. Here's the PTAM can track the camera, and here's the view from, so this is a little quadrocopter that, I don't know if you've met Jacob, he's doing a PhD in our lab, and in his master's thesis he developed this system. It's a quadrocopter that has a front-facing camera, which is now occluded here, and you see that what it does is he runs PTAM to estimate the camera motion, to give an estimate of where the camera is at any point. And one of the challenges in visual reconstruction is that when you use PTAM, for example, you never have the scale of objects. The way they do it, they have some initialization where you probably saw it in the PTAM videos, that they move the camera sideways a certain distance, and then the reconstruction is on that scale. So there's some assumption, let's say, that it's a handheld camera and that the camera moved by, I don't know, say a few centimeters, so that gives you the scale. You say the first baseline I just provided by hand. And then things are automatic. Here what we use is these quadrocopters have multiple sensors on board. They have the camera, but they also have, for example, an ultrasound meter that measures very roughly the depths. But that is a rough measurement, but it is an absolute measurement. There is a scale that we get in this way. And then the major challenge that Jacob solved here is, first of all, not only to get PTAM running on the quadrocopter. It communicates with wireless, with the base station, sends the images down, and the laptop laptop computes the pose estimate, the camera estimates using PTAM, and then sends that back up as a control command. But the major challenge is to fuse the multiple sensor information. So in particular, what he did is he had one estimate of PTAM about where it thinks the camera is, then one estimate of the ultrasound meter, the height estimate to the ground, and then there are so-called inertial measurement units, IMUs, or gyroscopes that you have on your smartphone that determine rotation, etc. And so you can use all of these and fuse them in a so-called Kalman filter to get an estimate of where is the quadrocopter. And the challenge is you have to accurately model the delays. In a multisensory system, not all sensors have the same speed. So the images come at roughly 15 frames a second, but then you have the PTAM processing on top. So if PTAM gives you an estimate of the camera motion or the camera location, is of course not the current camera location, but a while back, whenever the images were acquired, right? And so you have to keep track of an accurate timestamp, because then if you measure the ultrasound depths, that measurement is faster, and so the depth measurement cannot be directly combined with PTAM. You have to model these delays exactly to keep track of what measurements refer to the camera location at which point in time. But that can be done. It can all be integrated in a Kalman filter, and this is what you have here. And so if you ever want to see a real demo of this, just contact Jacob. He's happy to show it to you. It runs very robustly, so we often, maybe you may have already seen it at TUM Open Day, we like to show that demo. It's very popular. You can really, as you see, interact with the system. At this point, the challenge is to stay in that one spot that we marked afterwards. And like a little dog, it always comes back to that one spot. Even if you cover the camera, move it away, once you open the view again, it comes back. And so here you see what the nice feature of one of the main advantages of a real-time capable SLAM system. So if you do visual SLAM or visual structure in motion, and you get the estimates of your camera in real time, you can do amazing things. You can have these fly around autonomously. What Jacob has already done also is to have it fly certain figures, so you can, as a user on the computer, define a figure like a house or a square, and then the thing flies off exactly the predefined pattern. What we have not done, of course, is one of the next steps is to do autonomous navigation. That would involve obstacle detection, obstacle avoidance, path planning, things like that. That would be some of the next steps. What we have done, I am not showing it here, but I could show you later on if you're interested. We have done reconstruction from the quadrocopter. Because one of the things that also companies are interested in is you want to recover the geometry of rooms. Architects, for example, are often interested in that. You come into a building, you want to know, what does this building look like? And here what you can do is you can put sensors, cameras on top of the quadrocopter and use these cameras to fly the quadrocopter autonomously and use them to recover the dense geometry of the room. And we now have techniques where we can just hit a button, the thing takes off, and in a matter of seconds you have a model of the entire room. Yes?
If in the reference plane this image something changes,
That's a good question. So if we go back, well, sorry. So the question if something changes in the reference plane, if you go back to Pitam, it is actually fairly robust to that. Sorry, this is Rome and Dubrovnik, here is Pitam. If you look at the second example, applications of Pitam to reconstruction, of course here there's nothing moving, but here you have a car moving, right? It still works. Or in the other example, here's a car going through the scene, and here, for example, it reliably tracks, although here in the background you have a lot of structures moving very differently. And it says moving stuff outside the window doesn't bother the system. Yes?
What is the red or thing in the beginning? Whenever it starts to track something, there's this red orange.
Yes. This is the initialization phase of Pitam. He typically moves the camera sideways until and tracks points until he has a certain baseline, and then computes a stereo estimate that is for initializing. That way you get an initial estimate of 3D points, and then he tracks these over time. Same here. And that is, in some sense, the Pitam we found is fairly robust, but there are some issues that are sensitive. The initialization has to work out, etc. But here you see there's a substantial portion of the image plane that moves very differently. But then it's slightly blurred, so the key point approach is not going to actually find feature points there much.
The initialization should be from side to side.
Yes, yes. What I recommend, if you have the time, if you're interested in this, Google Pitam, download, install it, try to get it running on your computer, maybe use some handheld camera, and then experiment with it. And then you get the feeling of how reliable it is, how sensitive is it, how well does it work. We found that there are some issues it is sensitive to. In our quadrocopter approach, we can compensate for the shortcomings of Pitam by using multiple sensors, by using the ultrasound measurement, by using these inertial measurement devices, and by fusing all that information we get reliability. We can, in some sense, stabilize Pitam in this way. For example, we can have a scale estimate that is difficult just from images to estimate the scale. So we can circumvent these shortcomings of Pitam by using multiple sensors in combination. But it is robust, so coming back to the question, if there are structures that move in the scene, it is fairly robust to these, but it depends on how much is moving. Of course, if the entire scene is moving and if the dominant part of the scene is not static, then it's going to at some point break down. Yes. More questions?
In the learned 3D map of the quadrocopter, how accurate is the position? Is it like in centimeters?
It is as accurate, I would say, as what you get with Pitam, more or less. It is more robust because of the multiple sensors, but about as accurate. And I would guess, in principle, it should be about pixel accurate. But in the paper, that is Jacob's IROS paper, this is the annual robotics conference of last year, you can go to the paper. There's also follow-up papers by now where we quantitatively evaluated the performance. I don't remember, but he had some ground truth experiments where he checked how accurate it is, and then you can check. But in principle, the good thing with vision-based approaches is you should, just as accurate as you can track points, you should be able to localize the camera on that same accuracy, pixel accurate in principle. The reason why it hovers a little bit back and right is actually a little bit more due to also the control. How accurately can you control? This quadrocopter is a €200 quadrocopter, so the control commands are not fulfilled super precisely also. So there's a lot of little errors on that level. Yes, and one of the challenges that we're looking into is, can we still do that for smaller quadrocopters? It turns out nowadays you have quadrocopters of that size that can fly around, and we're currently working on porting these technologies to small ones that are more flexible. But the difficulty is you probably need higher frame rate in terms of control. It's very much like a fly, you know, they're very sensitive, and the small ones, I'm pretty sure you open the window and they fly out because of the air, you know, it's very much like flies. So these bigger ones, they have more inertia, and so they're somewhat easier to control actually than the little ones. All right, so that's all. Thank you very much.